Now, post-Moore era is quite a buzzing term. Do you believe customized processor, which is closely associated with silicon geometry, would be very disruptive for the Moore's law?
To some degree, Moore's law held well for a very, very long time, for decades. But certainly the cost issue, these days, very, very few silicon manufacturers can afford to build a wafer fab with a leading geometry. So the costs have been going up exponentially. And the smallest process nodes, it's only really companies like TSMC, Samsung, and Intel who can afford the investment in the absolutely latest wafer fabs. There is another law which is less well known, which is called Dennard scaling. Now, one reason why Moore's law was successful was that if you went into smaller silicon geometries, you generally also reduced the power supply voltage. And with Dennard scaling, he predicted that if you reduced the size of the transistors and you also reduced the power supply voltage, the power density would remain the same. So in other words, your chips would not overheat by going to a finer geometry. Now, Dennard scaling began to break down in about 2005, when transistor leakage became significant. Up till 2005, you could more or less ignore transistor leakage, and you only worried about the dynamic power consumption. So already in the last 15 years, Dennard scaling has broken down, which has meant that maximum clock frequencies really haven't gone up in 15 years. So this has been a challenge. 15 years ago, most systems on chip would have a single main processor on them. We've seen that people have addressed the need to increase performance. They've had to do it without increasing the clock frequency. So the way they've done that is to put multiple processor cores on the chip. So for example, in a mobile phone, typically there would be a multi-processor configuration with, say, 4 application processors. There would also be separate subsystems with embedded microcontrollers for handling something like Wi-Fi or Bluetooth or other communications. And there would probably be some DSP processor in the modem. So the workload has been spread out among many processors, and you've been able to increase the performance that way. However, even though these processors have been a bit specialized, they are still fairly flexible. So how do you get even more processing performance? Well, you will certainly need some general purpose processors still, like for running an operating system, but the only way to increase performance in specialized tasks such as artificial intelligence is to create very specialized processors. People talk about domain-specific accelerators, which are programmable devices, but they are optimized to run a relatively narrow set of tasks. So they may be optimized to run something like an artificial intelligence inference algorithm or a particular graphics application like ray tracing. So the way to increase performance in the future is going to be to create many different types of specialized processor. Now, this is a big challenge because it means you need a lot more design work to be done. And at Codasip, we see 2 ways of solving that problem. One is to have efficient design automation. One of our foundational technologies is our Studio design tool, which allows you to create a processor design very efficiently from an architecture description language. The other thing is, for things where an existing processor core may be fairly close to what you need, but not exactly what you need, there is the possibility of taking an existing design and customizing it, particularly if you're using RISC-V with the possibility of custom instructions. You may be able to take an existing RISC-V core and add some special instructions which allows you to improve the performance on a particular application.